All right, so we're going to talk about probability. There's actually four different types of probabilities that we're going to refer to. Well, I say four different types. I guess really it comes down to it's two types and two subtypes, if you will. So the first one is mutually exclusive, and that's the first thing we're going to deal with. So when we say mutually exclusive, what it means is that the two outcomes, the two sets of events, don't have any overlap between them. So an example to this would be if we want to know the probability of rolling a sum of 3 or rolling a sum of 5. Okay? And what we're referring to here is the fact that those two events do not ever overlap. There's never a time when we would get a sum of 3 and a sum of 5. So that means they're mutually exclusive. They never coexist together. So the easiest way to do this is if you have the ability to look at the actual outcomes. Rolling dice, there's only 36 outcomes when you roll 2 dice. So we can actually look at the outcomes, and it's very accountable. We can see that we have 36 total outcomes, and we can actually count how many of which type we have. For instance, a sum of 3. Well, let's find the sum of 3 here is 1 and 2 and 2 and 1. That'd give us a sum of 3. So that's 2 different outcomes out of 36 possible outcomes. And then we do the same thing for rolling a sum of 5, which occurs 1 and 4, 2 and 3, 3 and 2, and then 4 and 1. So that's 4 outcomes. So 4 out of 36, which gives us a total of 6 out of 36 outcomes, or 1/6. So the probability of rolling a sum of 3 or a sum of 5 is 1/6, 1 out of 6. However you want to write that. You could also do the decimal, which is approximately 1.6. Not 1.6, pardon me, 0.16. Okay? So that's mutually exclusive, meaning the two events never co-occur. Okay? There's never a time when they both occur at the same time. You're never going to get a sum of 5 and a sum of 3 at the same time. Okay? Now, if we do this a little differently, let's talk about it being a mutually inclusive event, which means that there is an instance where the events occur at the same time. So there's this overlap between the two sets. So the idea being is that when we say they're mutually exclusive, was there's no overlap. If we were to do the intersection of A and B, that'd be an empty set. Never occurs. There's nothing that they both have. Okay, and when you think about how we count this up with our sample space here, 1 and 2 and 2 and 1 were not part of the set that included the sum of 5. Those are different sets of different pairings of dice rolling. But with this, we're saying that there are instances where it does occur at the same time. So you're saying, well, when would that ever occur? Well, let's talk about this. Let's do the probability of an odd sum, or the probability of rolling a 1. Not a sum of 1, just rolling a 1. Well, if we look at all our possible outcomes here in our sample space, we can see very quickly that an odd sum occurs here when we have 1 and 2. That gives us a sum of 3, which is odd. Rolling a 1 occurred there as well, which meant that that was a place where we had 1 already in there. So automatically from the get-go, we see that this instance, we do have times when there is something in that intersection between those two sets. So what we need to do in this instance is we're going to need to deal with the fact that we have the probability of A occurring, we have the probability of B occurring, and then we have the place where we've counted it twice. So that is why we're going to do the probability of A plus the probability of B, which we've already established works for mutually exclusive events. But then we're going to need to subtract off the overlap, and that's what this is. The overlap between the two occurrences, the two events. So let's figure out the probability of rolling an odd sum. And I'm not pausing as I go through this dramatic effect. I'm pausing so you have time to actually add them up as we go. And you feel free to pause the video and replay as needed. So 1 and 2, 1 and 4, 1 and 6. So that's 3 of them, right? So that's 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12, 13, 14, 15, 16, 17, and 18. So 18 occurrences of odd sums. 18 out of 36, which is half, which makes sense. We would expect there to half all the sums to be even or odd. So we could actually ask that other question quite easily. Now, the occurrences of when we get a 1. How often do we get a 1? We get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's when we get a 1, not a sum of 1, but just a 1 in general. But we're missing something. 1 and 1 occurs twice. So there's actually 2 ways to get that to occur. That occurs twice. So we're actually going to count it twice. 12 out of 36. Okay? Now, what we need to do is subtract the overlap. Now, the way we do that is we're going to need to go through and count how many times does that overlap occur. And this is going to make it a little bit more clear why we counted this 1 and 1 twice, right? So if we count the overlap that occurred here, here, and here, 1, 2, 3, 4, 5, and 6. Those are the places where the overlap occurred. Now, maybe it's not obvious to why we counted it twice still, but think about this. I counted 1 and 2, 2 and 1, right? Same numbers, different order, which is why we counted 1 and 1 twice to get 12 instead of 11, because it's 1 or it's 1, which is a really boring sentence, but that's what we're doing there, okay? So it's 1 or it's 1. That occurs either way with those two things. So it's 2 occurrences with that, even though it's the same piece there. So now we have to subtract out those outcomes. How many outcomes were there? There were 6 out of 36 total. So when we do that, 18 plus 12 minus 6, so that gives us 18, and 12 gives us a total of 30, minus the 6 gives us a total of 24. So it's 24 out of 36, right? So this works really well. This process I'm going through works really well when we're dealing with countable sets here. We're going to go into other times when we can deal with things that are a little bit less easy to count. But another aspect of this that I do want to mention is the fact that inside of inclusive events is we have independent and dependent events. This is a whole nother scenario of things we need to talk about. And we're going to talk more about these in detail in a little bit. But I do want to point out the fact that what we're doing here with this plays a huge role in that, right? So we got the probability of A and B occurring at the same time when they are independent. Dice rolling is independent. There's never a time when rolling the one dice is going to cause anything to occur with the other dice. Playing cards is dependent. I play out the ace of spades. I'm not going to play out the ace of spades again. So so the next card that's played out after that first card is going to be dependent upon what the first card was. It's going to change the probability of the next event because of what the first event was. So dependent events are actually handled a little differently than independent events. So let's think about this right here in terms of here's that overlap, that independent overlap. That's what that and is. That's that intersection between those two. Okay, so if we think of it in this terms, the same thing, probability of an odd sum or rolling a 1 with either dice, because that's what we're saying there is rolling a 1 with either dice. That's 18 out of 36 plus 12 out of 36, because that's that first part, just adding those two pieces together, and then subtracting the overlap. The overlap is the intersection between those two sets, which in this case, if you go by what this says, it is 18 over 36 times 12 over 36. And what I'm suggesting is that these two events give us the same quantity. So the easiest thing to do is to look at this one and say, well, is that 6 out of 36? So let's see. There's some reduction we can do here, but I'm just going to use my calculator for the first go around, and then I'll do a second go around to kind of show you a little bit more of the workings. 18 times 36 times 12 divided by 36 gives us 0.16 repeating. Math fraction. It's going to convert it to a fraction of 1/6. So sure enough, this is 18 over 36 plus 12 over 36 minus 1/6, which is equivalent to 6 out of 36, which gives us the same value of 24 out of 36. Now, if you didn't have a calculator, you wanted to use this by some other, to simplify that by some other means, 18 out of 36 is 1/2. 12 out of 36, that's 1/3. Just divide both top and bottom by 12, right? So that gives us 1/6. So there's a really easy way to do it without a calculator. And a lot of these things can be done that way. Just using fractions actually makes a lot easier work of this a lot of times. So anyway, they were the same thing. And that was all I was doing there, just showing you that really quick. It does actually give you the same thing. Now, this isn't a proof by any means, but it is a numerical demonstration of that it does actually work. We're going to go into more detail with this in class and with other examples in other videos. Thank you.